Thank you, Ernest. I'm very excited to be here today. First, what is Quickwit? So Quickwit was created in 2020. I co-founded it with Paul and Adrian. So I'm a co-founder. I'm not the CEO. And what we are doing is a search engine dedicated to logs, and we do everything in Rust. We are enjoying that since the beginning. And so we are very happy to share what we have done since last year. And I will uh, I will let Evans continue. So tonight we will present you three parts of what we are doing. The first part will be presented by Evans. It will be on our cluster membership algorithm. Secondly, Harrison Burt will present what he has built on top of TanTV. TanTV is the core library of Quickwit, so it's the search engine, the core engine of Quickwit, and you can build many things on top of it. And lastly, I will present the architecture and why our Quickwit architecture is very good for logs. So, Evans, I'll let you continue on ChitChat.
Thank you. I'm really excited to be here. And just as Francois said, my colleague, I'm Evans, and I've been around the Rust community for a while. I'm software engineer at Quickwit right from the beginning. And today I'll be presenting about ChitChat, which is how decentralized cluster membership implementation in Rust. So to start, let's try to first understand what's cluster membership management is. On the in Quickwit context, it is a subsystem for managing a fleet of application nodes, and it provides us horizontal scalability like Quickwit Search service. There are other services we currently don't support, but we will be supporting very soon in a couple of releases. And it also provides knowledge about Node, what they can offer, like services, disk availability, and so on. And aside from that, it also provide failure detection, like when a node is down, what are nodes that we don't need to try to connect to because they are down. And this also can be useful for client libraries, especially when a client library has a view of the cluster. It knows what is going on in the cluster. It can really decide and do client-side load balancing and really lot of clever things. So these are the things that motivated us to first try to introduce a feature in a cluster membership management feature in Quickwit. And we developed it and named it ChitChat, and ChitChat has two major components along with other nice things. So the major components currently, as of today, are Scuttlebutt Algorithm implementation, which manages the membership which is the membership algorithm, and we have another algorithm implementation that is fee accrual failure detection, which takes care of the failed nodes and telling us what are nodes that are alive. And we have other goodies inside this library for easier integration and testing, because this is a networked application. Then we kind of need to be able to simulate real world scenario for testing. So prior to implementing ChitChat, our first few version of Quickwit had a cluster membership feature, but this was implemented using S.W.I.M, which stands for Scalable Weekly Consistent Infection Style Process Group Membership Protocol. But then we decided to move away from it because the pros for that is it's definitely faster if you compare it to what we currently have on the paper, of course, and it's used in HashiCorp products. HashiCorp have a notable product called Surf, which is an implementation of S.W.I.M, and it's really battle tested for many years. Unfortunately, we could not find in the Rust ecosystem an implementation that is really close and battle tested to serve. Or we have some couple of implementation, and some of the implementation were not really library oriented, like not really built to be reused. We found artillery. Artillery was really good for us, and that's what we used for a couple of times. But the problem with artillery was it was not giving us the level of confidence we really needed. And the other con is like S.W.I.M is really hard to implement on itself, so we felt like it will be challenging to take that route. And also real world implementation like Surf, for instance, is very limited, and HashiCorp had to develop and research few extensions that they called under the name Lifeguard to be able to mitigate some of the problem you encounter with S.W.I.M. And so we came up to search and decide to go with Scuttlebutt, which is implemented in ChitChat. So Scuttlebutt has a paper titled Efficient Reconciliation and Flow Control for Anti-Entropy Protocol. The nice thing about Scuttlebutt was, for us, it's easier to understand and implement correctly. It allows nodes to naturally share information like service port, available disk space or RAM, and which is really nice for our use case. And also, it is an algorithm that is battle tested in production grade system. It is actually the one as Apache Cassandra uses. The cons is like, if you compare to the previous S.W.I.M, the way it gossips is slightly slower than how S.W.I.M work. So both of them, Scuttlebutt gossip with a technique called anti-entropy, and then S.W.I.M gossip with something called rumor mongering. So the key difference between anti-entropy and rumor mongering is that with rumor mongering, the cluster, a node in the cluster will share information with all the node it knows about. I think the word all is very important here. Whereas in anti-entropy, a node will just select randomly a few nodes to share information with. So this this means that because of the number of nodes selected to share information, propagation goes really faster on when you are using rumor mongering in S.W.I.M compared to what Scuttlebutt uses, which is anti-entropy. Another key difference is that when anti-entropy is started, anti-entropy selects random node, but it keeps running perpetually as long as the cluster is running. On the other hand, when you are doing remote mongering techniques, when a node starts sharing information, at some point in time, the information is declared as obsolete, and then node stop sharing that information. And that is one of the key differences, because at this point, this is where S.W.I.M becomes complicated, because it's very hard to decide when at which point you need to decide, okay, this information is really obsolete. If you decide too early, there will be some node in your cluster that don't get that information, that update, and then they are lost in the cluster state. And if you decide too late, then you have been consuming a lot of resources and just doing work for nothing. So that's why we feel like anti-entropy has a good stance in that. Because for anti-entropy, you keep sharing the information perpetually. The only thing that changes is when the information there is an update onto it, the new information, the new update gets shared across the cluster. So let's go a bit deeper into Scuttlebutt and how it works. So Scuttlebutt, in Scuttlebutt, a node keeps a map of node ID to node state. And node state is like a version key value pairs. A node is only allowed to modify its own state. So it can have the global state, but it can only update his key space. And a node can share other node state as well. When it gets, let's say node A gets an update from node B, it can share those updates. And this is the way all node eventually gets all the cluster state into their own local state. So if you look at the Rust, the Rust code, you have here a portion of the code that is a cluster state, and then you have seed node, which we will talk about, and then you have node state, which is a node ID, and then the node state. And you have on this slide, there's a serialized version of a node state. So if you focus on the part which says node state, you have the node ID here, and then sorry about that. You have the node ID here, and then you have the key values. So the key values can contain anything, and this is where we felt like it's really nice because you can share any information about this particular node to all other nodes. You don't need to declare to create a special kind of messages. You just need to change your state, add this information to your state, and then all the cluster, the other node in the cluster gets to notice it. So how Scuttlebutt gossip? Again, as I said, every second a node randomly selects a few nodes to gossip with. And to make things a bit smarter, we randomly select a seed node if not already, and then also we randomly select a dead node. And this is in case when a node is declared as dead, we kind of probe it from time to time to see if this node is back online. So a quick note is that the gossip frequency and the number of selected nodes are configurable through Scuttlebutt. And seed nodes also are nodes that are known to be highly reliable within your cluster. So you know that these nodes are almost always available. You can trust them, and they can be used when you are starting a new node. You tell them, hey, contact this seed node. You will get most of the cluster state information from it. So practically this how the gossip round is made of. Let's say node A decide to make a gossip round with node B. Node A has to compute a kind of digest, which is like a summary of all the information it has. And when it computes the digest called digest A, it sends a SYN message to node B that contains that digest. And when node B receive that SYN message, it computes a delta using the digest. So it kind of computes what it thinks like node A is missing from its current state here, and then it also calculates its own digest. Then what it does is it replies node A with a SYN-ACK message by adding its own digest, which is digest B, and then the delta. When node A receives that reply, the delta is what node B thinks node A doesn't have. So node A needs to apply that delta, and then node A is going to compute another delta, which it thinks, which is the amount of information it thinks node B is missing from its own state. So it computes that delta using digest B, and then send an acknowledge message with that delta in. And as soon as node B receives that delta, it applies it. And that's the end of the gossip round. You will see that the message SYN-ACK, and acknowledge follow the same pattern as three-way TCP three-way handshake message type. So on top of that, there are quite question to ask. How about faulty or slow node, right? In most distributed system, node gets their presence notice via heartbeat. Scuttlebutt with gossip protocol already provide heartbeat via two ways: direct heartbeat between A and B, for instance, where node A gossip directly with node B, or there is also an indirect heartbeat. So you have node A, while gossiping with node B, share node C latest state. So there is, you will notice that there is no specific message about heartbeat. The heartbeat is almost like, just like I showed previously on the slide, the heartbeat key value pairs. A node just increments his heartbeat counter, and that update is considered as an update, a state change, and that state change is propagated across the cluster. So every time a node sees an update from the heartbeat counter, it knows that, okay, this node is there, it's heartbeating from my point of view. And that is how heartbeat actually works. So that's why you have direct heartbeat and indirect heartbeats. And so this leads to the fact that when a node stops sharing update, its state is just left alone. So how can we get the list of live node or dead node in the cluster? when can we confidently mark a node as dead? You could probably use timeout, but the problem with timeout is it's really hard to find a good timeout. So this is where the second part of ChitChat implementation comes in, which is fee accrual error detection. And this is an algorithm that calculates the fee value based on a window of recently received heartbeat interval. So when we receive a heartbeat counter from a node, we store the timestamp, and then next time we receive another heartbeat from that node, we calculate the difference, and then that difference we store it in a window in an array where we have a lot of interval for that particular node. And by calculating this fee value, it really approximates nicely, taking into account network delays, packet loss, or application performance fluctuation. And based on the research on the paper, the best value is usually between 8 and 12 for the fee. And that's the best fee threshold. But usually it's really good to try it on your workload and then know what value works really best for you. And a quick side note is, like, we are talking here about fail stop failure, not Byzantine failure. So we assume that all the nodes in our cluster behave correctly. If they say they have stopped, this means they have crashed, they have stopped working, but none of the node is lying to us. Like, we don't care, we don't treat that kind of failures here. So this is a figure representing the window, the heartbeat interval window. And as soon as it crosses that window, the previous one are dropped. So the fee value is the time elapsed since last heartbeat divided by the mean heartbeat interval. So once you have the fee value, you can confidently declare a node as live or dead, as long as the fee value has not crossed that threshold, it's still considered as live. That's the most part of ChitChat, but then there's still things that remain. There are still things that remain, whereas integrating it with Quickwit nicely. Some of our requirements include for Quickwit include, we want a fresh local state for a run for every run of the node. We don't want a state just overriding new states because it has lower versions. We want other running node to detect that a newly started node state prevailed all its previous states, because if you shut down a node, for instance, and then you restart it, it might come back with overriding things. We want node to be able to advertise in their public gossip address, because this communication happens on UDP, and then in an environment like Kubernetes, this is dynamic. You don't really know the address IP prior to running the stuff. So we want to be able to compute this, and then so that a node can advertise on which port, on which address it is communicating. These are the things we want to share. We want also a node ID to be the same across subsequent run. So whenever, like for local disk, this is important for us to keep cache data because we do search across object storage, and this is really nice to have. So our solution consisted of making an identifier for a node and making the gossip public address configurable, probably asking the user to configure it or extract it to compute it, extract it from the environment, an environment variable when we are starting the node. And then also, most importantly, make the ID part of the ID static. By extracting part of the ID, by making part of the ID static, we make sure that that part we can extract it and map it to a physical node where we can solve our caching problem. So the solution comes to this. The node ID in Quickwit is then made of a node unique ID, which is chosen by the user who is setting up his cluster, and then you have a node generation that comes next to it. And the node ID is the static part, and then the node generation is just a monotonically increasing value, which is a timestamp. And Apache Cassandra also uses a timestamp for that. This solution is quite simple and avoid us a lot of trouble. No extra measure is needed to avoid old state from overwriting new state, because when you start a node, when you restart a node, because of this node generation that gets incremented, you obviously have a new ID inside the cluster. Our implementation also stays close to the paper. We don't need to develop any extra layer or any extension. And then using the timestamp also make sure our Quickwit node are stateless. We don't need to store something on disk and then later restart it. So this is something we really care about, especially for environment like Kubernetes, where deployment we don't want user to be managing those we want to keep our node stateless. So aside from that, we have other goodies that comes into ChitChat. You have the garbage collection for obsolete node. If you remember from the previous slide, anytime you restart a node, you get a new ID, which means the previous ID is just left alone there inside the cluster state. This can get out of hand very quickly. So we have a garbage collection of obsolete node that detects when a node is declared obsolete, is dead, and it has not been used for a while. We kicked it out from the cluster state. We also have a transport layer abstraction for network to test it, because this is a network application to be able to test it thoroughly. So this is basically what we have in terms of the presentation. I think the time makes it really difficult to stitch all the information we can have. But if you are interested, we have a blog post about it that goes more into details. We also have the repository. It is open source. So we also have the repositories under GitHub/Quickwit. You will find under ChitChat. So you can go there, and why not, you can also contribute and give us feedback on those lines. So thank you for listening to me. I think my time is up. You might be hearing it. So I'm open for questions.
Thank you very much, Evan. Any questions from the room? We'll go from the room first, and then we'll read out some questions from anyone on the chat.
Hey, thanks, Ernest. With choice of technology, did you look at using console? I think you mentioned at the start you're using some HashiCorp tech. And also, if you can run this on Cube, why would you not use etcd or something built in, or does your protocol work within the Cube discovery?
So first of all, that's a great question, and we at some point we thought of using console and the HashiCorp stuff, but that will mean using some software as sidecars, and this is not something we really wanted. We really wanted something self-contained that adds much more like a library that we can add things on top. To make it work as of now, like, yes, console or any other application could have worked for us, but then down the road it could have made things much more difficult for us to implement all the cluster features we want. And I think I really mentioned it. That's why we went with Scuttlebutt, because it is simpler for us to understand and get right. So we can be prepared for changes, the upcoming changes.
Okay, so
I hope that answers your question.
Thanks. Can you hear me?
Yes.
Yeah, so I'm just curious, how do you test in the face of randomness? You mentioned, obviously, excuse me, you have some non-determinism and randomness. So how do you test, how do you sort of model and run through failure scenarios in the presence of randomness?
In the randomness here is introduced as to where we select the GOSI protocol selects nodes. And so this is really self-contained from the algorithm point of view. Now, if we are talking about in terms of network failures, and that's why I said we have transport abstraction, we have normally UDP communication, and then we have another one that use channel, and we use the channels to test. So we probably have like tests like we declare a percentage of messages that can be lost for when we are setting up the test. And then when we run the test, we definitely make sure that number of packets, those number of messages get lost across the test, and we do our expectation and see how much rate we have in terms of how speed we have, how the message this cluster state get propagated, how other node gets noticed that a node A is dead within the cluster, or how when a node join, how quickly that node gets noticed within the cluster. And we have some threshold expectation within a time bound period that we run assertion on. So this is how we kind of set up our randomness in terms of testing. But in terms of node selection, this is something that really is self-contained within the algorithm. Though we have some tests to say, okay, you can select this to make sure that internally it works. But for the integration test, we have we run scenarios in terms of how much percentage the packets are lost, and how are we doing in terms of performance, and how accurate we are in terms of declaring a node as dead, whereas it is not actually dead, or it is indeed dead.
Anyone else? Any more questions before we go to the chat in the room? All right. You're right. Okay, Nish, could you unmute yourself, and if there are any questions in the chat, could you read them out, please?
Sure. No questions so far, though.
No questions? Okay, all good.
So,
sorry, do you want to go ahead, Evan?
Yes. So yes, these are the references from this slide. I will share the slide afterward, and then you have everything that's and the repository link on this slide as well. So feedback and discussions are all welcome on the repository, because this is something we open to the community as well. So we will like feedback. We kind of we are eager to see other people using it inside their project, and then giving us feedback, so we can take it forward and probably make it a bit like the way Surf is today in Go community. Make ChitChat something like that as well in the Rust community. So thank you for your attention.
Great. Last shout for questions. Okay, we've got one last question. Right.
Hi there.
So, other way around.
Where is it?
Other way. Yeah.
Ah, there you go. You said on one of the first slides, seed nodes are selected based on some criterion. I don't remember the word reliability or whatever the word was. Is that like a static or dynamic criterion?
Okay, so seed nodes are more like when you set up your cluster, you kind of have an overview of your own cluster. You know, you kind of have some nodes that you particularly rely on. You feel like, okay, these are the nodes, they are always on, and these are the nodes that we call seed node. In terms of selection, then when you select, probably I can go back onto the slides. In terms of selection, when you select, we are trying to say the way the gossip work is every second it selects a few nodes, and it can be 5 right now. Like the default configuration is usually 5. Then we need to make sure one of the node that's among that selection is a seed node, and one of the node randomly is a dead node. A seed node is simply a node that you as the setup owner, you know, okay, this is a node I can rely on. It rarely goes down. It rarely goes down, and this is where I'm saying about what I'm saying about highly reliable, because that's your own point of view, not necessarily Quickwit or ChitChat point of view. You know that this node is reliable, and this is your reference point basically on your cluster.
When you say highly reliable, they have to remain highly. They basically set once, and they have to on some fixed criterion. They have to remain highly reliable through the.
No, that's not definitely it. Like you can shut it down, you can update it. But what I'm trying to say is when you have a cluster, it's kind of speculating, okay, when I need to start a node or I have a node A, for instance, and I want to join a cluster, there are probably some nodes that have been running for a while. And those nodes are the most reliable nodes that have the cluster state, that have most up-to-date cluster. So if you you have a cluster, you just join a node A, and then you want to join node B, then you say, okay, node B is joining through node A that just joined. It might happen that node A still has not got all the cluster state, and this is a bit problematic because then it needs to wait a bit longer. It will eventually get the cluster state, but the only problem is it will need to wait a bit longer before getting all the update. Whereas if you join a node that has been there for a while, this node is there is much more probability that this node has a better view of the cluster state, and then you get all the data, all the cluster state from you have. And one thing I want to add about that is like the UDP protocol has a limit on the packet size. So what we end up doing is, if the update you are getting is larger than the UDP packet size, we can do partial updates. So we send part of the update of the cluster, you get it, and for another gossip round, it can be from the same node or from another node, you will get the remaining update from the cluster.
Thank you.
Yeah.
Right. So another round of applause for Evans. Thank you very much. And Evans, share your social media if anybody wants to ask you any further questions.
Yes.
Carry on chatting in the virtual room as well. So yeah, share your details to let people know where they can ask you some follow-up questions.
Okay, so you can find me on Twitter. I will put that in the chat on EvanXG852000.
Great. Okay, thank you very much. One round of applause.